Hey everyone, today's Saturday, October 9th. Hey everyone, today's October Saturday 19th, 2024. And today we'll be discussing what I'm pretty sure is the first 5% tornado risk of the fall. I guess not counting Hurricane Milton, which was less than 2 weeks ago. We have a slight risk of severe storms in New Mexico. This is not really going to be a forecast video. It's going to be more of a real-time analysis, given that storms are already ongoing and we already have a tornado warning today. Right now it's about to be like 5 p.m. Mountain Time, I'm pretty sure. But anyway, here's our 5% tornado risk going from Interstate 40 here in New Mexico all the way down to Carlsbad. And also in a similar area, we have 5% for hail and wind. Given our current satellite view, we have storms ongoing, supercells ongoing. One of them just got tornado warned. I think this is our first tornado warning of the day. We have a radar indicated tornado warning near Fort Sumner. Like I said, this video is going to be more real-time analysis about what's been going on now that we have our first tornado warning. Here's our radar. And if we go to radar velocity, we have a pretty nice tornadic signature. It's radar indicated. We have winds going towards, winds going away. And if you just close this circle, we have counterclockwise circulation in this storm. A quick radar 101 is green is winds going towards the radar over here. Red is winds going away from the radar. So just making a circle around it. We have nice counterclockwise rotation, cyclonic, tornadic rotation in this supercell storm, which is why it's tornado warned. A lot of these storms have this kind of. This one has a tornado signature. We go to storm velocity. You can see we have pretty much the same thing on this one. We have winds going towards. We have winds going away. So we have anticlockwise, counterclockwise rotation. Now going back to radar, like I said, here is our wide view of all these storms going across eastern New Mexico. Going up to our water vapor satellite, we can see we have a low pressure system here in Arizona that is providing our synoptic lift. Then we can go to 500 millibar charts. Here, 500 millibars. You see better. We can see it better here. Here's our low pressure in Arizona. Here's our storms ongoing in New Mexico. If we go to 300 millibars real quick. Here we have lots of divergence going on in the upper atmosphere. I basically have this notepad of like a checklist to check the possibility of a tornado going all the way from step 4 of forecasting clouds, aka rising air. And like I see, that pink that I showed earlier is our divergence, basically meaning that here's the surface. We have divergence in the upper atmosphere. We have air that's separating, leaving a vacuum, but we can't have vacuum in the real atmosphere, so we have air rising. And Meteorology 101 says warm air rising, it cools, condenses, and it forms clouds. So basically here we're just forecasting our clouds is step 1. So we have divergence in the upper atmosphere. That's a check. Another way is we want to check our surface. Here's our surface, our most recent surface observations. Here you see winds coming from the southeast. We have moist air. We're in the 60s dew points. We're in the 60s and low 50s. And over here we have winds coming from the northwest, and we have dew points in the 40s. So I would say here we have a boundary. Somewhere around here is our boundary. you know. So basically our boundary is dividing two different types of air masses. We have northwest wind. We have northwest air at 40s dew points colliding with southeast air in our 50s dew points. So we have air here converging. And again, another way to have rising air is you have air converging at the surface. And because it's converging, has nowhere else to go but up. And like I said, right before I erased it, here we have our convergence here, just going through the tip of western Oklahoma, western Texas right here. And we can see this in our satellite view. If I go to satellite, if I erase this real quick, you can see, because here's the tip of, here's basically the boundary, and that's why storms are forming ahead of it in the moist, in the 60s, in 50s and 60s dew points, area east of the boundary. So that's step one. So we confirmed that we both have divergence on the upper atmosphere, and we have convergence in the lower atmosphere in the surface because of a boundary of a Pacific front going through New Mexico. Now here's our NAM model. Going for this time, we zoom in. So here's our low pressure. Here's our upper low in Arizona, expanding all the way through New Mexico. We zoom in through New Mexico. We can check where our boundary is, which is basically where our dew points are being divided. Is somewhere around here-ish. Somewhere here is where our boundary is. You see right here we have 50s dew points. We have mid to high 50s. And behind it we have 40s dew points. So here's our boundary. So if I would check some soundies, our forecast soundings is going to give us, our forecast soundings is going to give the information for this information to keep checking our checklist. So let's take a sounding. Currently our storms are ongoing somewhere around here-ish. So let me take a sounding here. So here's what the NAM is outputting for around this time in eastern New Mexico. Here's our forecast sounding, which is basically our best guess of what the atmosphere is looking. Here on the red and green is our temperature and dew points throughout the atmosphere. At the surface, we have a 65 temperature over 57 dew point, and we have deep moisture going up into the atmosphere. And the way we could check if we could get thunderstorms. Okay, we have deep moisture. So like I said, we have deep moisture extending up into the atmosphere. That's a check. And lapse rates. Our lapse rate is how fast our air is cooling the way we go up into the atmosphere, which is this down here. Our surface to 3 kilometers. That means our first 3 kilometers, per every kilometer we go up, the temperature is dropping 7.2 centigrade. And here from about 3-ish to around 6 kilometers is 6.7 Celsius per kilometers. So anything over like 6.5 is considered an unstable atmosphere. So here we have adequate lapse rates for thunderstorms. Like I said, basically here we have our 65 temperature at the surface, and by here we're already at freezing temperatures. Around 3-ish kilometers up into the atmosphere, we're already at freezing. So that's a very fast drop off of temperatures, indicating an unstable atmosphere. Basically, an unstable atmosphere is warm at the surface and colder air temperature aloft. And another way we can measure our instability besides this is just our atmospheric instability, but our partial instability. That means the instability of our rising air, is these levels, and you can see right now they're in the thousands, which is adequate instability. Anything over 1,000 is good for, usually. It's just a rule of thumb. It could be lower, it could be higher, but just a rule of thumb is anything in the thousands is good for an unstable atmosphere for severe weather. So here we have 1041, which is good. And there's no inhibition. This is our inhibition, which is basically like our anything over negative 30. So when I mean over, I mean like negative 40, negative 50. Anything over negative 30 is meaning that there's like a warm layer above the surface, which is preventing storms from going up. But here it's saying that there's not really a warm layer. So these storms are just able to rise freely. Meaning we get deep thunderstorms. We get deep thunderstorms, which is more conducive for more severe weather. Like I said, we have adequate lapse rates. We have adequate instability. We have deep moisture. So that's a check for thunderstorms. We have an adequate environment for thunderstorms. Now, supercells. Supercells are just longer lasting rotating thunderstorms at the mid levels, not rotating at the surface and like the low levels. There's a rotating thunderstorm at the mid levels, which is good for severe weather. And the way you forecast this is deep layer shear. Now going back to our sounding, our deep layer shear is measured by this numbers right here, especially the surface is 6 kilometer and our effective shear. Here it's saying that our surface is 6 kilometers at 39 shear knots. Basically meaning that it's our surface is 6. So at our surface, we have 15 knots coming out of the southeast, and at 6 kilometers right up here, we have around 40-ish knots coming from the southwest. So 15 at the surface, 40 at 6 kilometers, that's a 39 deep layer shear. And anything over 30 plus is for supercells, is for rotating thunderstorms. So here we have 39, 34. So that means that these thunderstorms, once these turn into thunderstorms from these factors, once this shear is going to turn those thunderstorms into supercells. So supercells, besides tornadoes, is good, conducive for hail and gusty winds. So here we have a radar indicated tornado warning, which is coming from a supercell, and it's indicating 1.50 inch hail, ping pong size hail. Here we have ping pong size hail and 60 mile per hour wind gusts. So yeah, so that's verifying so far. So we could check our supercells. Now to forecast tornadic supercells, means supercells capable of tornadoes, we need low cloud bases, low level instability, low level shear, and curved photographs. Now low level cloud bases is basically how high the bottom of our cloud is from the surface, that distance. So here's our surface, here's our cloud, and that distance, the lower our cloud base, the better it is for tornadoes to form. So the way we measure that is this, the LCL. The LCLs are lifted condensation level, which is where our clouds start to form. So basically our clouds form here, and they go all the way up until they reach here, which is the equilibrium level. So our cloud will be this high. This is our height of our cloud from 1 kilometer up to 9+ kilometers into the atmosphere. And here we get them in numbers. So here's our LCL at 883 meters. So anything under 1,000, 1,500 is good for tornadoes. So here we have 888 LCL. And our LFC is basically when our our lifting air keeps getting warmer than our temperatures in the atmosphere. So that's basically another proxy for instability. And here we have our LFC at what is that? That's 1,800. So anything under 2,000 is typically good for tornadoes. So here we have good LCLs at 800, good LFC at 1,800. Now, that's a check mark on our low cloud basis. Now, our low level instability, that's the instability. Let me erase all this. That's our instability at the lowest 3 kilometers of the atmosphere. So that's our 3 cape. Like I said, cape is our instability. Like here's our overall cape at 1,000, and our 3 cape is 76. So anything, rule of thumb, anything over 50 is good for tornadoes. And here we have a 76 3 cape. So that was a check on our low level instability. So we had good LCLs, and now we have good low level instability. So now our low level shear. This is our SRH. And basically this is our winds changing in the lower parts of the storm. Like I said, a supercell is our rotating storm at the mid levels, at the 0 to 6 level. Actually, I'll just make it dry. A supercell is a rotating storm in our mid levels, but our low level shear is good rotation in the lowest 3 kilometers in the lower part of the atmosphere, which is better for tornadoes. And these are these numbers. And here we have a 177 SRH, 238, 228. Anything over 100, 150 is good for tornadoes. So rule of thumb. So 177 is good. Anything under 200 is good. 238, 228. So we have good low level shear for tornadoes. And like I said, just basically shear is our change of wind direction with height. So at the surface, we have winds coming out of the southeast, and at like 3 kilometers, we have winds coming out of the southwest and change with direction and speed. So at the surface, we have 15 knots, for example, and at 3 kilometers, let's say we have 30. So that's our wind shear, direction and speed. So we have good SRH for tornadic supercells. And one way you could visualize this is looking for curved hodographs. Now, hodographs is basically just a graph, like kind of like a connected dots of how our winds are changing with height. And so what it means by curved hodographs is hodographs curving in the lower levels. They get this R shape. And that's basically what's happening in this photograph. We have like a hook / R-ish shape. So this is indicative of a lower level of our low level shear. So putting all together, we have low cloud basis check, we have low level stability, we have good low level shear, and we have curved hodographs. So that's a check for our tornadic supercells, which is why we got our 5% tornado risk, and why we're getting tornado warnings in eastern New Mexico. And it's already like we're closing in on the late afternoon to evening, but our high resolution models were showing supercells, which are these what these like lines coming out of these storms are signifying is where it was indicating supercell storms in the late afternoon to evening, which is basically what's happening now. See here we have supercells ongoing. This is gonna be this is basically gonna be like a deep analysis. Let's try to see how deep we could get. Let's say here's a more closer look on our upper level low, which is giving our synoptic lift, our large scale lift. Here, like I said, we have an area of divergence. Here are ongoing storms in northeastern and eastern New Mexico over an area of divergence, which is these pink colors. Here's our surface. Here's our pressure at the surface. You can see there's like this, they're kind of curving to this faint U shape, which is basically where our boundary is. Like I said, in the warm side of the boundary is where we're getting these storms on the warm side. Okay, the warm side is our areas with high dew point our high dew points. So we checked our surface observations. Here we have on this side we have 50s dew points. Behind here we have 40s dew points. Our moisture convergence basically are an area where, like I said, convergence is where winds are coming together. So moisture convergence is basically an area where winds are coming together and they're nowhere to go but up. So they're converging, and that's basically rising air. You can see here areas with blue is where we're getting convergence. A better way to check this is deep moisture convergence. So yeah, that's just red. Anything, and it's red on, you can see it because it's messy. So here, red is convergence, green is our moisture, deep level moisture. So you can see that's why the storms are forming here, because there's convergence indicated by the red, and they're indicated by the green. There's deep moisture. So that's why we have thunderstorms forming here. Velocity, tension, magnitude. Velocity, tension, magnitude. Usually when it's like in lines, like these like faded greenish lines is where like it's kind of sometimes good for forecasting, like, I mean, not forecasting, but like analyzing where fronts are, aka boundaries. You can't really see it right now, but there was like a better like way to find the front we have here earlier. I can't really see it right now, but that's why you use different methods to see it, like our pressure, like dips where I was saying that it's kind of curving downwards. That's one way. Here at A50 temperature advection. Usually, one of the things I had on my notepad is warm air advection. Is area you can see rising air happening, and you can see here we have like sometimes one thing isn't there, which is why you need these other like things to check. Like, we already checked that we have our boundary right here, dividing our drier air and our moist air, which is why we don't need other reasons to have rising air. But basically, you can see here in this reddish region, and is where we're having warm air advection, which is promoting rising air. Down here we have cold air advection, which promotes sinking air. Our vorticity advection is another way we could forecast rising air. You can see here we have vorticity is what I added, but in this specific case, it's not vorticity that's providing, it's upper air divergence and surface convergence. Our thermodynamics, like I said, our CAPE. Here we're getting CAPE in the, I could just click and then it will give you, if you double click, it tells you our like points value. Like here we're having 1600 CAPE, mixed layer CAPE, which is better for tornadoes. If this ML CAPE is at 1000 plus, that's better for tornadoes than any other CAPE value. Like there's different types of CAPE, like surface CAPE, there's most unstable, but ML CAPE is better for tornado forecasting, and here it's at 1300. So yeah, it has its own here, ML CAPE, mixed layer CAPE. It has its own page. Yeah, so here we have areas of 1000 CAPE down here in these storms. Which one was the one? I wonder which one was the one that was tornadic. It's one of these probably, and it's in this 1000. But like I said, these are rule of thumbs, and it also depends on terrain. So eastern New Mexico has like higher terrain, so it doesn't need that much CAPE to provide tornadoes, and sometimes, and this is better for like Central Plains tornado forecasting. Like I said, a tornado in Los Angeles, for example, which happened last year, it only needed less than 500 CAPE, for example. So if you were just checking for, check marking for, oh, this area has 1000 plus CAPE, that's good for tornadoes, but that won't work in Los Angeles. That might not work in eastern New Mexico. So yeah, our lapse rates, like I said, that's our how fast our temperatures is dropping in the atmosphere. We have a 6, so these are kind of like low, but here we're getting yeah, because we're already past peak daytime heating. So our max lapse rates are pretty good at 7.5 to 8 centigrade per kilometer. Our LCL height, like I said, anything under 2000 is good. So here we have 750. So yeah, here down here we're getting 2000 plus down here, that we don't care about that. We care about this. So here we have good lapse rates, LCL height, LFC height, anything under 2,000. I think I said, I forgot what I said already for this one. Like, let's say anything under 2,000. Yeah, here we have good. It's adequate. We don't get to 2,000 until over here. So here, over here, we're getting 1,500 to 400. That's adequate. You can check our QT, which is basically what this is. This is our QT diagram. Basically, you want, deep moisture and maybe some drying. The green. So green is our moisture. So basically, you would want deep greens going up high, and then maybe a little bit of drying, and then reds that don't overlap the blue. Blues are partial, at least in this model and this website. In this website, I think in the case of blue, in this case it's black line. But here we see it's good enough. Also, I forgot to check sin. Sin isn't on here, is it? Oh wait, yes it is. It's in this. So like I said, anything over negative 30, so negative 40, 50, negative 60. So here we're not in a capped environment yet, at least in our mid levels. So it's still storms are still in a good environment. Here we get into our wind shears. Like I said, 0 to 6. Anything over 30 is good for supercells. And yeah, we're in a good environment for that. We're going to double tap. Here we're in 0 to 6 is 43. Yeah. Our 0 to 1, anything over 100. So here we have, this is good. 0 to 3, anything over 200. But here it's at 170. But, it's still adequate enough. Basically, you can check those things. And these, so 0 to 6. Here's a new one. Oh, here's our helicity. I mean, I was talking about these. But here's our helicity is still adequate-ish for eastern New Mexico. So like anything over 200, anything over 250, 250, 2-ish, 100, anything over 50, 200 is in this one. So we're still in an okay environment. Here's our autographs. Like I said, anything where the pink and red are like an R shape, like here. Like a half circle, like here are bad lapse rates. The pink and red are in an R shape. They're like going straight up together. Again, here they are like in R to have circle looking shapes, which is more adequate for tornadic supercells. And these are composites, which is basically taking all these numbers and like just making like its own educated guesses. You can say this is a Hoyer is good for supercells, but like it's just breaking down these, like it's just combining all these parameters and making its own parameter. Like here, for example, it's combining MUK has to be over 1,000. Effective storm relative helicity has to be over 50. Sin has to be less than negative 40. And that's how it comes up with this number. But probably the better ones is, let's see, effective tornadic parameter is pretty low right now, except for these storms down here are using the lowest 500 meters of the atmosphere. Violent tornado parameter. Yeah. Critical angle is one of the better ones. Because let me see, what's a good critical angle? Anything around 45 to 135 is good for tornadic supercells. And the closer you get to 90, the better. So here, our critical angle is 67. So that's in between 40 and 175. So we're still in a good environment for tornadic supercells. Let's check the radar. Still nothing yet. We are getting golf ball size hail now and 60-mile-per-hour winds. Here in our multi-parameter field, one of the better ones is surface vorticity and 3 kilometer and 3K basically. And basically, surface vorticity is surface spin at the surface. which is blue, and then 3 Cape is the red, and basically anything overlapping is conducive, better conducive for, it's called the tornado cheat code, which is basically is a very good way to figure tornadic, like one of the best. Everything I've said that is good for tornadic supercells, but this is very good for like basically like low, or just like a high confidence, to give you higher confidence on which storms have tornado potential, like of actually having a tornado come out of them. And basically, all these storms have tornado potential, giving the surface vorticity and the 3 Cape. It's about to be 6 p.m. And we check our high resolution models. After 6 p.m., we're still getting supercells, but they're congealing more into a line. See here earlier in the day we have here earlier in the day we have storms that are kind of by themselves. Like this one's, there's like space in between this storm and this one. But as you get closer into the nighttime, you see all these storms like get closer together, which usually is going to wind down our tornado risk. So when we might be in the, once these storms start forming, right now they're pretty still isolated-ish. But the next couple hours, these storms are forecasted to form into a line, and that's when your tornado possibilities drop, and that's when you get your wind. But that's when you get your wind gusts. Let me check our wind gusts. You see it starts ramping up to 40 miles per hour.